Well, welcome. I'm going to talk here today about things that go bump in the night, and more specifically about black holes, dark matter, and dark energy. These are topics that I've found a lot of creationists, recent creationists, have doubts about. And I think some of the doubts are ill-founded. I'll try to go through the science here and go with it, through this with you, and so you can perhaps understand better why I think I'm pretty excited about some of these topics. I'll spend most of my time talking about black holes, probably half the time, a bit less time talking about dark matter, and only a little bit of time toward the end talking about dark energy. So the big question is, do these things exist? After all, black holes don't give off any light. Dark matter, by definition, doesn't give off any light. Dark energy, well, you get the trend going on here. These things are not visible. So people sometimes argue, say, well, we don't see these things. You know, seeing is believing. So if you can't see them, well, maybe they don't exist. Another tack that's taken was that many creationists get the impression that these things were hypothesized solely to salvage evolutionary ideas. You know, black holes were invented so because evolution was in trouble. Without black holes, you got to have it. And dark energy, dark matter, those were invented to save the Big Bang Theory or whatever, and you have to invent that to salvage all of that. Well, I won't deny that there's a component there, but I think it's putting the cart before the horse. We have to understand the history of these things and where they came from, and then how people decided to use those. So, to the question, do these things exist? Well, there are a lot of things I think you believe in that you don't exist. Like, for instance, do you all believe in electrons? Who's ever seen an electron? No one's ever seen an electron, but yet we believe they exist. You ever seen the wind? Sometimes my wife will look out the window, look at the wind. I'll say, I don't see any wind. I see trees doing like this, you know, but I don't see any wind, you know. You can't see it. Can you see the air? Well, if you can see the air, it's not a good thing, all right? Okay? You can't see air. It's transparent. There are plenty of things we believe in, but without seeing them. We can see the effects of them, and this indicates oftentimes in science that our evidence is indirect. Many times it's very indirect on these things. Okay, what about the suggestion that they're hypothesized to salvage evolutionary ideas? The confusion is that many popular discussions of these topics of black holes or dark matter are thrown into the discussion of how stars evolve, how galaxies form, how the Big Bang happened. And so they're discussed within the context of what we patently recognize as evolutionary ideas, and apparently people can't separate out the two. I'll give you an example right here. How often do you hear antibiotic resistance discussed in terms of evolution? Many times I've heard radio programs and discussions where people say, well, how do we know evolution's true? We see it all the time. Antibiotic resistance, a perfect example of evolution taking place before our eyes. Case closed, everybody go home, evolution's true. Well, it turns out there's a creationary explanation for antibiotic resistance. It has nothing to do with evolution. We can explain that totally apart from any true evolutionary changes. So we're going to be very careful. Just because people talk about evolutionary ideas doesn't mean, in conjunction with something, doesn't mean that we simply say, well, it doesn't exist. We'd be consistent. We'd say, well, antibiotic resistance isn't true. It doesn't happen. Well, we know better than that. What we need to do, and I'm going to try to walk you through this today, is to separate the physical data from the speculation that oftentimes is associated with discussion of these things. Let me step back a minute. How do we measure mass? What is mass, first of all? Mass is
material.
Okay, it's a measurement of how much matter that you have, right? That's basically what it is. And how do we usually measure mass? Well, we do it by gravitational attraction, don't we? Some of you each morning or each evening may measure your mass by stepping on the scales. And when you do that, you're technically not measuring your mass, you're measuring your weight, which is a force of gravity. So as long as the Earth's mass hasn't changed overnight and the fundamental constant of gravity has not changed overnight, then we're pretty safe in saying that if your weight's changed, your mass has changed. Hey, but if I gain weight, if I don't like it, I can just simply blame the Earth or blame the universe. I didn't change. Everything else changed, not me. And you could defend that position. Maybe not very well, but you could defend that position out there. Well, in astronomy, it's kind of difficult to get a star to step on some scales. All right, so what we do instead, we look at orbital motion. We have two. That's the reason why I do binary stars. We got these two stars orbiting each other, presumably under mutual gravity, and I'm measuring their weight at that point. And by a little conversion, I can convert that weight, just like a little more difficult than what we do on the Earth here, but I can convert that weight into a mass pretty directly. And so we can measure the masses of things in binary stars, for instance. Well, I got a little graphic here showing you a binary star in orbit going around like that. And I've sped it up tremendously, of course. You've got two stars. Normally you wouldn't see the two stars individually because they're too close together and too far away. Notice that one of them is a little larger and it's blue. That means it's the hotter star. And there's another star that's kind of red. And as we're looking at it, most of the time we see the light of both stars, don't we? But occasionally one star will pass behind the other, like right now the smaller one in front of the big, and now the smaller one goes behind. Front, behind. Front, behind. We call these transit and occultations. This is an occultation. This is a transit. Occultation, transit. It all depends on which one larger is in the front, which one's in the back. Now across the bottom, they show the integrated light that you get. And outside of eclipse, you see the light of both stars. The light is brighter. But when you go into eclipse, the light dips, and it dips again. And the deeper eclipse is on the right side. That's called the primary eclipse, and that occurs when the hotter star is eclipsed. And the secondary eclipse is shallower. It occurs when the cooler star is eclipsed because the amount of area blocked off is the same in either case, but the luminosity goes to the fourth power of the temperature. So the hotter stars always is eclipsed at the primary eclipse. You'd be amazed how many introductory astronomy textbooks get that wrong. So it's the hotter star in every case. Well, this is not a terribly interesting system because these stars are spherical, and stars generally are spherical because it's the minimum shape that gravity will pull them into. But the kind of stars I look at typically are close together, and when they're close together, they tidally distort each other. The stars are not spheres anymore. There's kind of a bulge sticking out on either one of them. They can get so close together that mass can actually slop from one star to the other, and that's when it gets really interesting, because we can actually see these things developing with time. Let me show you a little more realistic situation. This is where the blue star is more mass than the other one, and so it has stronger gravity, and it's tidally distorted its companion, the red star. It's no longer shaped like a sphere. It's got kind of like a cam shape spun in a third direction there. And notice there's like a little halo, little blue, light blue thing around the equator of the hotter star, the blue star, and that's what we call an accretion disk. Accretion disk, because matter accretes onto it, because matter is transferring from one star to the other. The gravitational pull of the blue star, it's a more massive star, is so great that it pulls matter off of the cooler star, the less massive star. But because of angular momentum, the mass can't fall directly onto the blue star. Instead, it falls into kind of a holding tank, a disk of material around it. And that material is a gas. It's got viscous losses, frictional losses. And so as it does that, it loses orbital energy and slowly spirals down to the planet. So that's kind of like a holding tank. And you'll see what it does. The different shapes of the stars and everything will kind of whack out the eclipse curves, and they have a very different shape than before. And the kind of stars I look at are like this. 40 years ago, when I first got into this, when we saw light curves like that, we just got out our crucifixes. That was just really bad. But now we have these great models that were being developed back then. We can actually apply a model. This is a piece of cake now. The other ones are yawners. We're even looking for asymmetries. The curves are kind of whacked out like this because it indicates hot and dark spots, and we model this stuff all the time. It's pretty easy, but 40 years ago, it was just in its beginnings of all of this. So we like these kind of systems now, my research partners and I do. So it's a cool sort of thing to do. And by the way, accretion disks are not just some wild ideas. We actually have good evidence that accretion disks often occur in interacting binaries, hundreds, maybe thousands of examples. I published a paper, I was a co-author on a paper 30 years ago where we had simultaneous observations spectroscopically and photometrically. I was doing the photometric one about 30 miles away from the other observatory, simultaneously at the same time looking at these things. So accretion disk, well understood phenomenon in eclipsing binary stars. It's been known for decades, well understood science. Okay, what about black holes? First of all, what is a black hole? Well, it's a massive object for which the escape velocity is greater than the speed of light. What do we mean by escape velocity? Well, if you take an object, say a rock or a baseball, and you throw it up in the air, it goes up, it falls back down. If you throw it harder, it goes up higher, it's in the air longer, but it comes back down. If you keep throwing it harder and harder and harder, faster velocity, you eventually reach a point where the thing will go up and it will just be loose to the Earth's gravity and never come back down. That speed for the Earth is called the escape velocity. It's about 7 miles per second, 11 kilometers per second, or about 25,000 miles per hour. Now, we got some good baseball pitchers like Aroldis Chapman, who can throw pretty fast, but he can't throw nearly that fast. So all of his pitches are coming right back again. But if you can launch things that fast, they can. We went to the moon with the Apollo astronauts. Indeed, we did 45 years ago. They had to launch them up to 25,000 miles an hour just to get out of the Earth's orbit to get out to the moon. That's called the escape velocity. Well, obviously, if our escape velocity from the Earth is 7 miles per second, the speed of light is 286,282 miles per second, we're not even close to being a black hole. You might think that black holes are kind of modern. It turns out they were first hypothesized by a guy named John Mitchell way back in 1783. Over 230 years ago was the first discussion. Now, he didn't call it a black hole. What he did is he asked the question, well, how small would the sun have to be in order for it to be for light itself not be able to escape? And he was astounded. It was just a few miles across. The sun is nearly 1 million miles across, so the sun's not even close. And then the famous French mathematician Laplace, a decade later, addressed it more fully. He actually did a better treatment than Mitchell did. Mitchell just the first guy that did it, and Laplace more deeply. And it kind of sat there for much of 150 plus years. It wasn't until the 1960s that people began to look at it in more depth. In fact, the term black hole was coined in the early 60s. I think around 1963 or 64 was the first terminology. And a lot of things started coming together in the 60s. By the end of the 60s, we had actually started finding evidence that black holes might exist. Well, how might you do that? Well, suppose you have a black hole with an accretion disk. It's taking matter. It could be from a companion star. It could just be matter nearby that's being pulled in by this thing. Now, the black hole is not that black ball at the center of that disk. The black hole is actually well inside of that disk, okay? It's a tiny little thing inside of there. And you've got this disk of material, and it's falling inward. You get these frictional losses, which, when you take friction, like I'm rubbing my hands together, they get warm. You rob orbital energy, and you turn it into thermal energy or heat. But as you rob the orbital energy, it falls inward. And so as the stuff falls inward, it gets hotter and hotter. The outer portion of that disk is kind of red and then yellow and then white. You're getting to higher and higher and higher and higher temperatures. As you fall down towards what's called the event horizon, which kind of is the boundary of this black hole, you can heat that gas up to very high temperatures, like 1,000,000 Kelvin. Now, getting 1,000,000 Kelvin temperature of a lot of gas is a hard thing to do. There's a corona around the sun that's that high, but it's very tenuous. So it gives off a little bit of X-rays, but not much. You have to be close to it to detect it. But in the case of the accretion disk, it's a lot denser than that, and so you have copious amounts of X-rays. So you look for X-rays coming from sources in the sky like this. Unfortunately for astronomy, you have to get above the Earth's atmosphere to do this because the atmosphere blocks it. Fortunately for life, it blocks it because otherwise it would kill us, all right? So it's good we have this atmosphere. Good for living things, bad for astronomy. But hey, we got rockets, okay? Not a problem. We can get above the Earth's atmosphere in my lifetime to do this kind of work and open up a whole new area of astronomy we didn't have before. Now, also, black holes, we believe, have very strong magnetic fields associated with them. And you have charged particles here because you're moving very quickly because you've ionized this gas when it gets heated this much. So these fast-moving charged particles interact with this magnetic field in a complex way, and it can cause a jet of two jets of matter and radiation to emit, usually perpendicular to the plane of the accretion disk, and that's what these two things with this blue and the spirally looking lines or this artist's conception are showing you. I want to be very clear about something. None of this radiation or matter is coming from inside the black hole. It's coming from a region just outside the black hole. I think sometimes when I give a presentation on this, people don't understand that. They think it's coming out of the black hole. It's not. It's coming from a region just above the event horizon, but it's caused by these interaction of those fast-moving charged particles and the strong magnetic field. Do we see things like this? Well, actually, this is an artist's conception, but in the upper left corner is a radio image made from radio telescopes. We think we see a disk there from the accretion material falling in, and then there's a jet sticking up. Sometimes you don't see both jets, sometimes you just see one jet. That's actual data. Up there, the object is GB 1508 plus 5714. You heard of that one, right? I'm not sure what the GB stands for. I have to look that up. But again, the 1508, it gives its right ascension in the sky. It's like longitude. And the plus 5714, that's the declination, or like latitude, 57 degrees, 14 minutes. That's how we catalog these things. And again, I have to look up GB and see what that means. All right. Types of black holes. Well, we've classified these a number of ways. We have what are called micro black holes. These would be very, very small. They may not be stable. Probably those really small ones would pop out of existence pretty quickly. Then we have what are called stellar black holes, and they typically be between 3 and 20 solar masses. I put a check mark next to it because I think we have good data that stellar-sized black holes probably exist. And then we have what are called intermediate-sized black holes. These would have thousands of solar masses. I think I mentioned in one of my talks the other day that I'm real good at coming up with ideas, only to find out that I'm a few years late on getting them. And about, I don't know, in the last 8 or 10 years, I thought about intermediate black holes. I thought, well, I kind of thought, well, why couldn't these things exist? Well, I started doing a literature search, and sure enough, people were already talking about them. I independently came up with it, but behind everybody else, they'd already done it. I'm not in this field, so I don't keep up that much up with it. But kind of nice that I anticipated what other people had already anticipated. It makes me feel like I'm thinking the right way, at least, even if I'm a little behind everybody. By the way, in the last year or so, they've actually put forward now some potential candidates of intermediate-sized black holes. So that's interesting. That's really interesting. But I won't put a check mark next to it because it's still pretty tentative. But then I'll put a check mark next to this. We think there are supermassive black holes. These have millions of times the mass of a star, of the sun, and we believe that these are lurking at the cores of most galaxies, including the Milky Way. There's a really massive, supermassive black hole at the center of our Milky Way. So you can understand why we have these different ranges here, and we only have data to support two of them, the stellar and the supermassive. Let me continue on. Let's suppose we have a binary star here. One is a black hole, and one is a normal star. The black hole, again, is at the center of that disk. You've got an accretion disk. Where's the matter coming from? We are tidally distorting and pulling matter off the companion star. It's a normal star. And that matter comes in as a bright spot on the disk where the matter from the incoming from the other star smacks into that accretion disk. And as it orbits around, viscous losses, frictional losses cause it to spiral in, heating up all the way. So the inner part of that disk is going to give copious amounts of X-rays off. And then you get possibly a jet or two coming off perpendicular to this thing. So we can look for those jets. Maybe more likely we should look for those as X-ray sources, particularly if they're in a binary star system. That would help out a lot. And we have found such things. So the best detection for stellar black holes is in close binary stars. That way you have material being fed to it all the time. If it's an isolated one, the detection is going to be a little trickier. And the other companion fills what's called the Roche lobe. A mathematician named Roche came up with this. It's a gravitational equipotential surface, and if the star expands outward to fill that up, that means that material on that outer surface gets free to kind of float around and even go through from one star to the other. That's how it feeds that mechanism of feeding material from one star to the other. So it's not a matter of the gravitational force pulling it off, but as the other star swells, fills its Roche lobe, and then it gets pulled off at that point. And we call this mass transfer, matter transferring from one star to the other. And mass transfer is something we believe we've observed many times in normal stars, the kind of stars I look at. I don't do black holes, but the physics is the same. The binary stars, the same sort of principles going on. I see mass transfer. Why can't we see mass transfer in these? The matter, as I said, falls into the accretion disk, settles there as a holding tank for a while. And it says, in physics, anybody here study physics much? We have what's called a steep gravitational potential well. We've got this function that goes way down like this, and as it does, it liberates that gravitational potential energy. It has to go into kinetic energy. And then it gets, we say it gets thermalized. It's orbital motion, which is very ordered, but then because of frictional losses, viscous losses, you rob that orbital energy, but it has to go somewhere. It goes into random motion of the particles involved, and that is randomizing or thermalizing the motion. You realize if you take a glass of water and you take a spoon and you stir it like this real fast, vigorously, you pull the spoon out, the water continues to spin around for a moment. Then after a while that spinning stops and it just seems to stop again. Well, what happened to that motion? You can't destroy energy. There's energy of motion there. What's happened is through random collisions, you randomize that motion, and we say we thermalize it. It turns out you've raised the temperature of that water just a little bit. Guy named William Prescott Joule in the 19th century actually rigged up an experiment with water swirling around, and he was able to show the mechanical equivalent of thermal energy, that it actually is the energy of motion. The sort of thing you learn in grade school science, he confirmed 150 years ago in this experiment. So it's a randomization of the motion. We thermalize it, we turn it into heat, we say. So it becomes very hot, and if it gets hot enough, it produces X-rays, and X-rays are very hard to produce in copious amounts. And again, here's another example of an X-ray binary. You've got the disk, the jets, that black hole at the center, and material being pulled off on the accretion disk, feeding the black hole. The black hole gains, as it gains matter, it continues to get bigger. By the way, there's kind of a tricky, quirky transfer. What's going on is some of the matter falls in, it liberates energy which powers those jets. It's the magnetic field doing it, but it's trading off energy. Some falls in, some. It's an engine. It's basically an engine. It's throwing matter inside that furnace of the black hole to power those jets to make it happen. Okay, we go out there and we look for X-ray binaries discovered by X-ray satellites and other above atmosphere, Earth's terrestrial atmosphere experiments. And since they are binary stars, we can solve for the mass. That's the whole point. It's like asking, getting back to my point, probably thought, what was the point of what I said about asking stars to step on scales? Well, if we have binary star, we're looking at orbital energy, orbital motion, we're looking at gravity. We can, from Newton's law of gravity, we can figure out how much mass is involved. Typically, when we do this, we get the mass not of the black hole, but of the whole system, the black hole and its companion star. So you get the mass together of the two. You might think, well, you don't know the mass of the black hole yet, do you? Well, yes, but we oftentimes can infer what the mass of the companion star is. If it's a main sequence star, we definitely can, because we know the masses of main sequence stars. So all you have to do is subtract the mass of the visible star that we can see and actually characterize and infer its mass from what we know about stellar astronomy, and then subtract that from the total mass, and what remains must be the mass of the object we're not seeing. Now I got to put a little caveat in here. I'm going to switch terminology. I'm not going to talk about a black hole right now. I'm going to call it a compact object. A compact object is just what the name implies, a very small but massive object. And a black hole is one possible compact object. But there's another one out there. The other possibility are what we call neutron stars. Sometimes the way we detect them is through pulsations. We had pulsars. In an earlier talk, I mentioned pulsars very briefly. Now what's very interesting is that there is a maximum mass that a neutron star can have. We think it's around 3 solar masses. We're not sure the exact value, but we know it's not much more than 3, if more than 3. So if we infer the mass of the unseen compact object in the system to be greater than 3 solar masses, it can't be a neutron star, and the only thing left is a black hole. So we believe the cutoff point is 3. If we can go out there and find examples of X-ray binaries where we've inferred that we've measured the total mass, we subtract off the inferred mass of the visible companion, and it turns out to be more or less than 3 solar masses, we can figure out what it is at that point. And we've done this. I'll give you an example. One of the first ones discovered was Cygnus X-1, and what that means, it was the first X-ray source discovered in the constellation Cygnus, and that was back in the 1960s. Turns out it's an X-ray binary. We see Doppler motion of the X-ray emissions from it. There are actually some X-ray eclipsing binary stars, believe it or not. The thing gets eclipsed for a while, and that's really cool because it tells us a lot more we don't know otherwise. When you subtract off from the total mass, the mass of the visible companion, you're left with 11 solar masses. Obviously, that cannot be a neutron star. Coincidentally, another object, V616 Monocerotis, that means it's the 616th variable star discovered in the constellation Monoceros, and it's it also has 11 solar masses. Again, it cannot be a neutron star. It must be a black hole. And there's a whole list now. It's in the scores at least, maybe more, maybe hundreds now. I'm not sure. But, you know, astronomy textbooks, ones I used to use teaching at the university, they gave several examples. I remember the last book I used, it had like 15 examples of various ones, and it was not exhaustive. So do we have some good data to support the idea that black holes exist, stellar-sized black holes? You bet we do. We got good data to support this. Well, what about supermassive black holes? Well, we think these are lurking into centers of galaxies, including our own. There are some mighty peculiar things going on in the cores of galaxies. Our own galaxy is difficult to probe because of all the dust obscuring it between here and there, but we can probe it with other wavelengths that can penetrate the dust. We can see into the galaxies, other galaxies nearby, and the Hubble Space Telescope has been very useful in that because you're above the Earth's atmosphere, and it helps us to probe deep with high resolution the center. And what we see are orbital motions of stars and other objects near the center. These things are moving around something at the very center, moving very fast, very short periods in a very small size. So if we measure how fast they're moving, how fast they're orbiting, we assume it's orbital motion. Sometimes we see matter going this way on one side and this way on the other. Think of Doppler radar. They can now have the technology now for years. They can do radar. They did that at least since the 50s and 60s. When I was a kid, they could tell you where rain was falling and maybe kind of intense. That's all they can tell you. But with Doppler radar, they can see there's this rainstorm over here about 40 miles away, and on one side of the storm, the raindrops are blowing this way at 60 miles an hour, and a short distance away, they're blowing away at 70 miles per hour. Automatically they know that it's probably doing this, and it's probably going to pick up speed. It's going to turn into a tornado. And by the way, by the differential motion, they can tell you which direction it's going. Fortunately, in this case, I set it up, it's going away from you, okay? But that's not too good for the people over there. You know, they can issue warnings now. When I was a kid, when they issued a warning, it was because there's already one touchdown. It's kind of late at this point. But now they can anticipate a few minutes out, maybe 20 minutes even, and say, well, there's a tornado warning in this particular area. And it actually saves lives. Same thing going on here. If you see motion on either side, it's almost certainly because there's orbital motion involved here. So, we can then take that size, we see the orbital size, we can take the speed and we put it into what we call Kepler's third law of planetary motion. It works well. We can derive it in a general sense from Newton's laws of motion. It's basic physics. I used to teach at the university all the time. And this will help us find the mass. And when we do this for the cores of galaxies, we find oftentimes it's in the millions of solar masses. If there's something that's millions of times more massive than the sun, it ought to show up. Yet we look there and there's nothing there. Also, it's confined in a very small area. And so if you start doing the numbers, there's no object that we know of outside of a black hole that can fit in such a small volume, particularly when it's not giving off any visible radiation. So that's the smoking gun we have here, that there are black holes lurking here. These also, black holes of this type have been invoked to explain a whole range of what I call exotic objects. These are AGNs. Those are active galactic nuclei. Those are galaxies for which there's unusually high emissions coming from the cores of their galaxies. And then QSOs, those are quasars, quasi-stellar objects discovered back in the early 60s. And what we have here is an object that, if the distance is correctly inferred from the redshift they have, you got an object that's pouring out maybe 100 times the energy of the power of the Milky Way galaxy, a galaxy that contains a couple 100 billion stars. Something that's pouring out 100 times more energy than that, and yet it's doing it in a volume that's probably no bigger than the solar system. So, I mean, it's incredibly bright, incredibly small, and again, the only thing we can think of that will work is a supermassive black hole with an accretion disk and those jets operating. You're sacrificing some matter to go in to feed this inner engine that's driving this. Oftentimes they have jets associated with them too. Like for instance, here is a nice image of the M87. It's a relatively nearby acting AGN. It's a globular, it's an elliptical galaxy, a very big one, by the way, at the core of the Virgo cluster, probably 30 to 50 million light years away. And you've got this jet coming out of this thing, and we believe there's probably a super energetic thing there powering this thing. And the clumps of matter in that jet, we can actually measure the speeds of these things, and they're moving at an appreciable fraction of the speed of light, like 80% the speed of light. It's incredible. So there must be one whale of an engine inside of this thing driving it, and the only thing we can come up with is the supermassive black holes once again. Let's come back to home and talk about some more mundane, if you will, examples of these supermassive black holes. One is the object we call Sagittarius A star. SGR stands for Sagittarius. The A means it is the first radio source discovered in the constellation Sagittarius. This was actually discovered back in the 1930s. Probably was not named until the 50s. It was the first radio source identified, I believe, outside of the Sun and Jupiter. So extra solar system sources. The little star means that it's an appendage. This thing, it turns out, under higher resolution, has pieces, and this is just one part of it. Now, the object itself consists of a few things. One of them is an object they call S2, and it has an orbit. It follows a 15.2-year period of going around. It's a very eccentric orbit. It's, goes near and far, so it moves pretty quickly down here and more slowly, and it falls in, moves more quickly, and then more slowly like this. 15.2-year period, and its closest approach down there gives you some limits on how big this thing can be that it's orbiting. All right. From the orbital motion, we can infer its mass. By the way, its closest approach is only 17 light hours. 17 light hours. That's a little farther out than the most distant planet in the solar system. There are a few light hours, so it's comparable in size to the planetary system we have. And from the calculation from the data, we infer that it has a mass of 4 million times that of the Sun. So you're going to take 4 million suns and put it in the Sun, no bigger than the orbiting the outer planets of the solar system, and yet you don't see anything. It's not giving off any radiation. And if you do the numbers, like how big a black hole would be for that mass, it fits really well. So it looks like we have a black hole here. Its radius, again, is less than 17 light hours. It could be quite a bit less, but it can be no larger than that. Or consider the galaxy M104. Sometimes called the Sombrero Galaxy. It's also in the Virgo cluster. Its stars near its center are orbiting very quickly, and it would require 1 billion solar masses to explain it. That's one of the biggest supermassive black holes I know of. 1 billion solar masses, and there's nothing there to see. This is showing the complex Sagittarius A star down there, and a radio map, and the inset here shows you changes made over, 3 years time period. So a lot of this is done with radio measure. This is the photograph of the Sombrero Galaxy. You can see what's called a sombrero there. It's kind of a cool, I've seen it through a large telescope a few times, and you can see the dust laying in it. It's really, really kind of, not quite this nice, but it is cool to see. If you see photographs of it and look at it with the telescope, you'll know what you're seeing there. Question. I've been talking about this for 10, 15 minutes. Where's the evolution of what I said? I didn't discuss any evolution, did I? No, not a whit. Not a bit of it. This is a very good example of my point. We talk about operational science. You know that? It's the science of the here and now, how the world now operates. We also talk about historical or origin science. That's where the ideas of evolution or even creation come in here. But I've been talking about operational science. That's all I've been doing, giving you the data, giving you the observations. Here's how we apply physics as we know it, and this is the best explanation we can come up with. That's good operational science. There's not a bit of evolution in what I've told you here. So people, creationists who doubt that black holes are real, they have to realize that they're trying to shoehorn in some origin science here somewhere, I think. They're not looking at this very clearly. We, above all people, should be able to separate the operational and historical science, and I fear that many recent creationists fail at this point because they don't understand what's going on, I don't believe. Now, what happens is once you get the data showing that, operational science data showing that these things probably are real, then people want to ask the question, well, where do they come from? Well, that's a fair question to ask, but it's not the same as operational science to ask here. I mean, I could say, well, God made them that way, and it's no worse than saying this thing formed somehow. Well, at this point, there is no clear explanation for the micro black holes, and that's just as well. We haven't found any yet. So we don't need an explanation as long as we don't have any. But for stellar black holes, we believe they come from the implosion of the cores of very massive stars, an event we call a supernova. And a supernova can leave behind, at least this type of supernova, can leave behind either a neutron star or a black hole, depending on how much mass the remaining core remnant has in it. There's a dividing line there, and it really doesn't matter from the physics which one you get, but once you determine how much mass is there, the physics will tell you it's going to be one or the other. There's no origin scenario for intermediate-sized black holes. The best bet they have is maybe mergers. You form some black holes out there and then stellar size, and then they kind of merge into bigger and bigger, and they finally grow up into being intermediate-sized. And then there's no origin scenario for supermassive black holes. There have been some suggestions of mergers, but there's got to be a whole lot of merging going on to get from a score of solar masses up to millions or billions. Some people even suggest that there's some sort of unknown primordial process. Don't you love that? Some unknown mechanism in the early universe created these supermassive black holes. Oh yeah, that must be the case, scientists say, with their patches and their pipes and everything, and rubbing their chin like this. The problem is, that's merely conjecture. Just because a scientist conjectures something doesn't mean it's science, doesn't mean it's true. It just simply means they're conjecturing. So I love that. Some unknown primordial process created supermassive black holes, and that's going to somehow pass for science. Well, that's nonsense, okay? I'm not saying it couldn't have been some unknown primordial process. I'm simply saying, though, that that's not the way science is supposed to work. And again, I like to separate out the historical or origin science from the operational science. All right. Dark matter. As I defined it before, I'll define it again. Dark matter is this mysterious stuff that seems to be permeating the universe, dominating the mass of the universe, and it doesn't give off any light. It gives off, it betrays its existence by the gravity that it exerts on the gravitational attraction. All matter apparently is affected by gravity, but this thing doesn't give off any light, and that's really bizarre. People sometimes ask me, well, what's dark matter? What is it made out of? And I tell them if I knew that, I'd have a Nobel Prize in physics. It's that big of a question. I'm not going to deal with that much today. I want to talk about the physics of, or the reasons why we think it's there. Dark matter, you might think is pretty recent because it's all been a buzz in the last 2 decades or so. But the first mention of dark matter goes back to 1933. That's almost 90 years ago, 85 years ago. There's a guy named Fritz Zwicky. He was a Swiss-born astronomer, and he came to the United States and spent his career here. And he was observing what we call the Coma cluster. The Coma cluster of galaxies, I should say. There's also a Coma star cluster. When we say Coma cluster, it's almost always understood to be a cluster of galaxies. It's a few hundred million light years away from us. It contains a few thousands of galaxies. And what he was doing is he was looking at the motion these galaxies have. He could measure their Doppler motion coming this way and away from you. They're all kind of orbiting. And some were moving toward and some were moving away. If you make a large enough measurement of these things, and he did over the entire cluster, you can then take the average motions that you measure and you can calculate how much mass is required to hold it together because you're looking at orbital motions. It's like a binary star again. You're asking these galaxies, a whole cluster, to step on the scales, except the different kind of scales here being used with a telescope to do it. And it's the same basic physics all over again. So he determined the mass, what we call the dynamic mass of these motions of the galaxies in the cluster, assuming that they had bound orbits, which I think is a pretty safe assumption to do. And this is a robust result. And it's no different from how we measure mass any other way. If you're going to question this, you might as well question your weight when you step, your mass, when you step on the scales in the morning. It's that fundamental and that basic. But there's another way you can get the mass as well. What he did is he counted how much light there was there, and we figured this out, that if you have more mass, it's probably a lot of that mass is going to be in the form of stars, and if you have a lot more mass in the form of stars, you're going to have a lot more light, and so there should be a nice relationship between how much light a galaxy gives off or a group of galaxies give off and how much mass is there. And people have worked out the scale within the solar system, within the galaxy, the Milky Way galaxy. We do a census and we measure how much mass there is in a certain volume. We measure how much light there is, and we get this mass to light ratio. It turns out to be about 1 to 1. That is, for every solar mass of matter you have, you get about 1 solar luminosity of brightness. That's pretty cool. So if you measure up how bright a galaxy is, and multiply or divide by this mass to light ratio, if you do mass to light ratio, you multiply. If you do light to mass, then you divide. But anyway, you take that factor, you figure it in, and you can convert that to how much matter should be in that galaxy. And you can do that for all the galaxies, the whole cluster as a whole, and you get a lighted mass. Well, when Zwicky did this, he found out that the dynamic mass greatly exceeded the lighted mass by a huge factor. Now, one of the problems that Zwicky had was that he was seriously underestimating the distances to these galaxies, and we cleaned that up over the next couple of decades, but still it persisted. The gap wasn't nearly as great as it had been, but it was still pretty great, on the order of a factor of 10. And he repeated it for other galaxies, clusters, and every time he did it, he found the same result, that there was more mass required by the orbital motion than you could account for by the lighted mass that was seen there. And this became known as the missing mass problem. They called it the missing mass problem for probably 50 years. And by the way, astronomers just sort of said, that's interesting, rubbed their chins and moved on. Recently written a paper about this. I think a couple things happened. Right after this was the Second World War, people got pulled away, people lost, kind of forgot about it during that time. They were pursuing other things after the war. Furthermore, back in the 1930s, they were pushing the technology to the limits that they could do, and they kind of got lost for the next 30 or 40 years. And then in the late 60s, and in the 70s, they had newer detectors, could push the limit further again. They started reinvestigating it. Even then, it took more than a decade for astronomers to wake up and smell the coffee here. By the way, here's a photograph of the Coma cluster. Most of the objects you see there are galaxies. Like this is a galaxy, that's a galaxy, that may be a star. This is a galaxy. That brighter thing with the spikes on it, that's a star. Maybe at the top right there is, but almost everything else in there is a galaxy. There are thousands of them here, and this is just one of many thousands and tens of thousands of clusters of galaxies. You're starting to feel kind of small? Yeah, the universe is like that. They'll do it to you. Okay, well, in the 1970s, a couple of astronomers, Vera Rubin and Kent Ford, began looking at this particular galaxy. This is the Andromeda galaxy. We keep coming back to it because it's a real workhorse. It's the nearest galaxy of any size to us, comparable in size to our own galaxy, a couple of million light years away from us. And there's orbital motion going on in this galaxy, and I'll stand up to point this out. The objects on this side are, let's say, I don't know which side it is, we'll just say this side, are orbiting towards you. This thing is nearly edge on. It's tilted a few degrees. It's not quite edge on. It's not face on like this. It's tilted a little bit. And so things on this side, let's say, are moving towards you, and things on that side are moving away from you. So if you take a spectrograph and you go across the thing and start measuring velocities, you'll find over here that they're coming toward, and over here they're moving away from you. So far, so good. Now, if you parse it up and measure in the core of the galaxy down here, you'll find a nice linear relationship. As you move out from the center, it moves faster and faster. What's going on here is right on here, you don't see any motion because it's all parallel to your line of sight. Over here, it's in your line of sight nearly. You do have to correct this for the amount of tilt, but that's easy to measure and easy to account for. But within the core, there's a nice linear relationship. As you go out from the center, it increases with increasing distance pretty linearly. When you get out to the edge here, it starts to roll over. The curve does. And then it should start to drop off, because notice most of the light is coming from here, isn't it? Right in that core region. Once you get out here, the amount of light is falling off tremendously. So you would expect once you get out of the core region, the amount of matter is decreasing rapidly. By the time you get out to here, almost all the matter is accounted for. And by the way, it's a fundamental result in physics. When you're orbiting around this mass distribution of matter, whatever is orbiting closer to you is all that matters as far as your speed is concerned. So if you're right here in this region, only this matter matters. You get out to here, only this matter matters. You get out to here, this matter matters. As you get farther and farther out, you're getting more and more of the total matter. You can treat it like a point mass at the center. By the time you get out to the edge here, virtually all of the matter is being accounted for in the galaxy. So you can make these measurements along the way, and you can calculate how much matter there is within successive rings of this thing. Okay? Pretty clever stuff that you can, everybody understand what I'm talking about here. So they start making the measurements, and so Vera Rubin and Kent Ford look at this really starting in '69, but running through that by 1975. They really had something going on here. The curve out there ought to roll over and become what we call Keplerian. The motions ought to drop down like this as you get out far enough. But instead, they remained very high and very level, and even went up some beyond that. And this implied there must be a lot of matter out there, what we call the halo of the galaxy. All right? Now, I'll show you a plot here. As soon as she takes her photograph there, I'll show you the plot of what I'm just describing to you here. Okay, here's the plot. And what you have here is distance from the center. I'm only doing one side. One side would be away and one would be toward, but you can flip it over and superimpose it to get, and they match up pretty well, actually. But this is velocity, and down here's the core region. As you move out from the core, you'll see a nice linear relationship. As you move out from the core, the faster it moves, and then you get outside of the core, the light's starting to drop off very quickly. So when you look at the lighted mass, you would expect the curve to look like this, a dotted line. That's called Keplerian. And that is what they expected. And for a long time, people would go up here, get to this top of here, and they'd stop measuring because it's hard to make measurements out here, and they'd quit. What Rubin and Ford did is they went out here and started measuring stuff out here. And lo and behold, instead of coming down like this, it continued to go up and flatten out to great distance. And if you make the measurement of how much matter is right here, it's pretty good. You go out here, the amount of matter out here now is greater than what you found. The matter between here and here is much greater than the matter that you had out here. And as you go out, the matter gets greater and greater and greater. In other words, the bulk of the matter that you measure is way out in the boonies of the galaxy, not where all the light is. Let me go back to the picture of the Andromeda Galaxy. From this curve and the data analysis that you do here, you look at this, you'd say most of the matter is in here. And as you work your way out, less and less. By the time you get out to here, you've probably encompassed 90% or more of the matter of the galaxy. That's what you'd say just by the way the light is. But when you do the actual analysis of the orbital motion, when you get out to here, you haven't even when you get out to here, maybe you've done at most 30% of the matter of the universe, of the galaxy. When you get out here, start sampling all of it. So most of the matter is out here. Well, most of the light is in here. There's almost like an anti-correlation between where the matter is and where the light is. That's the problem. Again, most of the matter is out here where there's almost no light, and where all the light is, there's just maybe 10% of the matter. You see the problem there? And so there is an anti-correlation between where the light is and where the matter is, and where the matter is and where the light is. It just doesn't fly. And when you look at that, that's startling when you grasp what's going on here. So, dark matter. We can do it other ways too. We can do gravitational lensing of distant objects. That's the third way. The first way was with the clusters of galaxies Fritz Zwicky originally did, and then Rubin and Ford in the 70s started showing the rotation curves of individual galaxies. And by the way, they repeated it for other galaxies and found the same crazy result. It's pretty consistent. They have found a few galaxies that don't follow this. They behave themselves, but they're the minority. And by the way, the results they get, like 10% of the mass is what we're seeing, is consistent with what you find from the galaxy clusters. the same number. The two agree very nicely. And then you can also do what's called gravitational lensing. This was something that was predicted by Einstein's theory of relativity almost a century ago, but it wasn't confirmed really until like the 70s or probably the 80s. And now we can actually use this to probe the masses of distant objects in this way. Here's what's going on. Here's a diagram of it. There's a galaxy cluster called Abell 1689. This is another cluster of galaxies. These are very, very far away. We're talking like, maybe 1 billion light years away or something. These little things here are clusters, are members of that cluster. Now, directly lined up with it is a very distant object, a single object. And the mass of this cluster acts like a gravitational lens, and there are little streaks that you can see over here and there, little streaks like bullseye patterns. You see those little streaks all the way around, like little bullseye patterns. Those are multiple images of this distant object beyond. See, if we're here, the Abell cluster is here, and this distant object is way out there. The light comes through, it gets bent by the mass, the space gets bent by the mass of this thing, and it forms multiple images. From our understanding of the physics of the situation, we can see how much lensing is occurring, and we can actually calculate, compute how much matter there is inside this cluster of galaxies. So it's a dynamical mass we're getting based on general relativity. And when we do that, and we try to compare to the lighted mass, we still get that ratio of roughly 10 to 1. And this has been done as well. So we start seeing, again, multiple lines of evidence showing that there's a lot of dark matter there. So what is dark matter? I already told you, I don't know. I wish I did. There have been many theories put out there, and one by one we've seemed to have eliminated those different theories. Somebody suggested this kind of a particle. It turns out we look for it. We had things called machos and wimps and all these things, and one by one they are eliminated. And some people say, some creationists have told me, well, look, they did this experiment. They found no dark matter. No. They didn't find wimps. What they did is they eliminated one type of dark matter. They didn't eliminate dark matter, they just eliminated one of the possibilities. And this is very clever. There's something going on out there. By the way, I'm convinced that there's no place in the chart of particles, known particles out there. They have the standard model of particles out there, and it's filled in. The Higgs boson was one of the last ones they found. They fitted in the puzzle. If 90% of the matter consists of a type of particle which there's no room on the chart, then it just suggests to me the chart's wrong. So think about that. 90% of the matter of the universe is made up of a type of matter we haven't even dreamed up yet, and it's totally invisible. Do you find that way cool? I find that way cool. I find it humbling, and I find it exciting. And I think it would be very, very clever of a creator to do stuff like that, to give us challenges like that. So to me, instead of being a bad thing, I think creationists ought to embrace this. We ought to make this our own. And again, it's probably some form of matter we haven't even come up with yet. Again, I ask you, where's the evolution in what I talked about? Well, there really isn't any, all right? Now, I want to point out again, I can't emphasize this enough. So many creationists I've encountered seem to think that, these astronomers just made up dark matter to salvage all their evolutionary theories and such. And that's because they didn't start paying attention until about 10 years ago. But I've been around. And I was in grad school, and a lot of this stuff was coming together, and the astronomers didn't know what to do. Well, they looked at it, and their eyes popped open, their mouths fell open, and huh? What? And they were dragged screaming the whole way. It really wasn't until the 1990s that astronomers, after decades of being told you got dark matter, they said, you know what, I think dark matter does exist. It really took us a long time to come around to it. It wasn't like we ran headlong and just grabbed this, but once they became convinced that dark matter existed, then it became a lifeline. And so we have questions about galactic structure. Well, dark matter did it. You got questions about cosmology, about the Big Bang. Well, now the dark matter is just another free parameter. You got another free parameter you can throw around. So now they manipulate these parameters within the Big Bang model, within galactic structure problems, to solve these different issues. But again, keep in mind, the dark matter wasn't invented to do this. The dark matter came along because we got mugged by reality. The data of operational science said dark matter probably exists. Once you're convinced it exists, then maybe you can start using it. And if you know the true history of this, you're going to realize, no, we're not desperately trying to do this. There's good observational science supporting the idea that dark matter exists. Well, what about dark energy? Well, back almost 100 years ago, probably 100 years ago now, Einstein took his general relativity, applied it to the entire universe. He was steeped in this idea that the universe was eternal and a static universe. He found out when he applied his field equations to the universe that even if the universe was infinite, the universe should contract under its own gravity, come down and collapse into a very dense heap. And you look around, you see the universe isn't like that at all. So obviously, one out would be to say, well, the universe hasn't always existed. That would be one possibility. But he didn't do that. He was still tied into the eternal universe idea. So he threw in this term called the cosmological constant, which causes space to repel itself. And you kind of put it in a balance. You know, if space is repelling at the same time that gravity's pulling in, you get this steady state situation, and the universe is static once again. Well, pretty quickly when Hubble within a decade discovered the expansion of the universe, he realized he made a mistake and he retracted it, and that's set for 70 years. But in 1998 and 1999, a couple of teams of researchers found data that seemed to indicate that the rate of expansion of the universe is accelerating. And one team actually got the Nobel Prize in Physics a few years ago for that very important work. So people said, well, what's causing this rapid expansion, the acceleration of expansion in the universe? And they said, well, there must be some sort of field that does this. This is, we can describe things in forces in physics with fields. We have gravitational field, electric field, magnetic field. We have all these other fields we put in. It's field theory. It's a way of describing it. It's a property of space that does this, that produces these forces. We take the derivative, take the negative of the derivative, and that gives you, actually it's use the Del operator to do that, but it's in vector calculus to get this thing to work out. And this term is similar to Einstein's cosmological constant, but they don't want to treat it as a constant. It could be, but they want to treat it as a possible variable. It could be changing. And so they decided to call it dark energy. What they're doing here is they're saying, okay, you got this dark matter. We're going to also throw in dark energy because matter and energy are equivalent things. But actually, it's a totally different thing they're trying to do here. And it's also how much dark energy is required is extremely model dependent. And it becomes another free parameter within the Big Bang model that you have. And so I'm a bit suspicious of this. I'm very bullish about black holes. I'm very bullish about dark matter. But I think that there may be some evolution behind this whole dark matter thing going on, their dark energy thing going on. So your instincts may be right. Maybe dark energy is being driven by more by the need for that. There is evidence that the rate of expansion is increasing, but it's modest, and how much you need of dark energy is highly dependent upon the model that you use. This is a map of the, I think probably from the W map, I believe, of the cosmic microwave background, and they can use this to constrain how much dark energy. There isn't even dark matter, but the problem is, to do that, you have to filter it through a particular model of the Big Bang. You change your model of your Big Bang, you change how much dark energy you have, and so it's, again, very model dependent. I will point out again, I've pointed out in another talk, it bears repeating, these little light and dark spots, different colors are color-coded for hotter and cooler temperatures. They can explain some of these features, but this one feature over here, this is called the axis of evil, and that is unexplained at this point. They don't know what's causing that. This is called the great cold spot over here. They don't know what's causing that either. No explanation for either one of those. They kind of keep quiet about it, but if you want to, just Google those. You'll get probably more information you care. Here's a little plot that goes back a few years on this. This is probably outdated, but the current thinking, at least a few years ago, was that the mass of the universe, remember mass and energy and mass are equivalent things, the equivalent mass of the universe, dark energy dominates at 74%. 3/4 of the mass of the universe is in dark energy. 22% is in dark matter, that's most of the remaining quarter. 3.6% of the mass of the universe is intergalactic dust. 0.4% is in stars, planets, and people. So that puts in perspective all the stuff we worry about as astronomers, the things we think about in the universe, if this is correct, is only 0.4%. And we're kind of missing the big picture. This makes an iceberg look positively exposed by comparison to this. I don't necessarily agree with these numbers, but I would say probably 90% of the universe is unobserved at this point, and I think that is way cool on all of this. I think, final thoughts, black holes really stretch our understanding to the limits. It kind of takes it to the brink and just throws it off the brink, as it were. We don't know what most of the universe is made out of, but we have an incredibly immense creator to make stuff we can't even begin to figure out. And I'll leave you with that thought. Thank you very much.